Hello friends, in today's tutorial I want to boost your R skills to new and unprecedented heights by opening the door to the riches of Google Earth Engine data. Google Earth Engine is a powerful platform for geospatial analysis and visualization that allows you to access, process, and manipulate some 5 petabytes of satellite imagery and geospatial data from various sources. We can tap onto the riches of Google Earth Engine using rgee package in R that serves as a bridge between R and Google Earth. In specific, we'll be taking 3 steps. The first step will be to show you how you can register with Google Earth Engine services and then set up rgee to connect successfully your R to Google Earth Engine. The second step will be to get some sample data, which is going to be earthquake data from Google Earth Engine via R. And the third one will be to create an awesome 3D elevation map of Iceland overlaid with earthquakes. In our first step, we are going to register and then log in with the Google Earth Engine. So I went here to Google. I search for Google Earth Engine, and then I click here on Google Earth Engine. Now here, there's a very nice page that explains to you what is Google Earth Engine, what are the benefits it brings. But for us, we need the Get Started tab, which is in the rightmost corner of the screen. So we click on Get Started. And over here, if you don't have your Gmail account, you need to create one. So if you have your email account, you can simply click here. And then on the next one, you simply also enter your password. And once you do that, you are almost able to do it. You do need to also verify here your access through the 2-step verification, which I did from my phone. And once you do that, you once more just need to confirm by clicking on your credentials here, and you are then in. So here, once we are in, we need to register a non-commercial or commercial cloud project. So once more, Google Earth Engine also allows for non-commercial. So we can click here, and then what we want to use here is unpaid usage. But you do need to specify here what is your area. So you can choose among academia, government, profit, news, media, trainers, or no affiliation. So I just chose here no affiliation, click next. And then what you can do here, you can create a new Google Cloud project if you don't have one. So if you're just starting. So for the organization, you don't have any organization. So for here, what you can say, project is going to be called, let's say EE Milos makes maps. And this one is available. And then the second one is the project name. So here, for example, what we can do is Earth Engine satellite data. Actually, it can be anything. It doesn't need to be, a specific one. So once you are done here with filling out organization, project ID, and project name, you can continue to summary. Okay, so once this is done, this is the summary of your project. So my project doesn't have any affiliation. And this is the project ID and the project name. So I just click here on confirm. And then it's redirecting me to the code editor. So this project is now registered, and it's opening now the code editor where I can access my user interface for the Earth Engine. And once the page refreshes, here we are in Google Earth Engine user interface, where you can see several things. Well, first of all, you can see several boxes here. On the leftmost side, you can actually fetch some of the data here, and you can clearly see quite a few fields like agriculture, fire monitoring, elevation, hydrology, oceans, soil. Guys, this is a very rich source. I mean, it has 5 petabytes of data, and I'm so glad we are tapping onto it. Next to it, you can actually write your script in JavaScript and get the data, modify it, even visualize it here in this Google Earth Engine. And then next to it, there's a console which shows you the output. So we're not going to be using this user interface. Rather, we're going to be now installing a library which is going to help us communicate using our language, communicate with Google Earth Engine to get the data and then visualize it in R. So the most important thing here to get from this whole experience is the Gmail that you use to register to this service, because we will need it to, once we install rgee, to authenticate within R. We're back in R, where we are going to first of all install rgee package, which is an R client for communicating with Google Earth Engine using R programming language. And then we're going to be loading into this R session. So the easiest thing is to simply use install.packages and then install the package from cron itself. So rgee, and once you do that, simply run also library rgee, which is going to load this into your R session. In order for us to work with Google Earth Engine in R, we need to install Python. And for that purpose, we call to rescue the package reticulate, which translates essentially everything we send in R into Python so that we will be able to communicate with the Google Earth Engine, access the data, and then work with it. So here we're going to do install.packages and then reticulate. And then below that, we'll just do library reticulate. Once we have reticulate, we can use it to first of all see if Python is already installed on our system. And second, if it's not, we can use Miniconda to install it together with all the package dependencies that we need to work with Google Earth Engine. So first of all, we're calling reticulate here and then py available. So I'm going to just quickly show you that I don't have actually Python installed. So it says here that when I run py available, that it's false. So it doesn't exist. So I need to actually install it in order to be able to work with rgee and then communicate with Google Earth Engine. So for that purpose, I'm going to call again reticulate, and this time I'm going to be using discover config. So this will then actually install Python on my system. So I'm going to just quickly show you the terminal when I actually run this. So once I run, as you can see, it wastes a bit. And then it shows here actually, yes. So now we have the Python. So the Python that is here that is installed is 3.8. And then it shows also here where you can find it and also the architecture, and also NumPy is there, which you will need. So again, as I said, it's going to install also the dependencies as NumPy. It also provides the NumPy version as well. Going back to this piece of information about the whereabouts of the Python, we should actually take this first path where it says Python and then copy it, because next thing we'll be gonna creating an environment where we will be using this rgee then to communicate with Google Earth Engine. Okay, so our next step is to install this Python environment from which we can work. So for that, we're going to be using rgee, and then most of the or all of the commands in rgee start with ee, which is Earth Engine. So it's quite easy to learn them. So here, what we're going to do is install and set py environment. So the first one is the py path. So this is the path to your Python executable file, the one that we just previously copied. So you should actually put it here, and it should be in the form of a string. So that's the first argument. And then the second argument within this one is the name of the environment, which is a generic one, and it's called rgee. As you run that chunk of the codes, you will be asked to actually restart your R session so that all these updates and changes can take place. So here you simply need to select the one and then click enter. So you're installed rgee, and we are almost ready to use Google Earth Engine in R. But first things first, let's first check if we have installed all the dependencies that are necessary to work with Google Earth Engine from R. So first of all, because this is a fresh version that I just opened, I still need to do library rgee. So this is gonna again load the package rgee, and then I can go here back to step 5. So here I'm gonna call rgee, and then I'm gonna do ee_check. Okay, so this is gonna check if I have everything that is needed. So let me actually run this and show you how this looks like. So it's gonna do now a check, and after a while, it's gonna say that the Python version is okay. We have version 3.8, more than enough. Python packages, NumPy, and Earth Engine API, they're all installed. And then I'm gonna go to the part which is gonna help me initialize the connection between my R here and Earth Engine so that I can finally fetch the data and start working. So in order to do that, you need to use rgee, and then you need to use ee, and then here initialize. So within this one, you should specify your user credentials. So remember, this is the Gmail that you use to log in into the Google Earth Engine. So again, you need to specify here as a string. So this is going to be just my Gmail. Okay, and once you write this, you can run this code. So what we'll do here is basically it's going to ask you to authenticate. So it's going to open here. It's going to say here, hey, please enter verification code. But at the same time, it has also opened a window where you can actually fetch your verification code. Okay, so here is my authentication. It says here that this is my account. This is the project name. Data access is use a read-only scopes. And then the next thing I need to do simply here is click on generate token. So once I do that, I will be able to get the verification code. But first things first, I need to actually click here on my credentials to authenticate myself. Okay, so continue. And then once you have this, you can click, select all, continue. Okay. And once we do this, you will see the authorization code here at the bottom of this page. So you simply need to copy this authentication code, and then you go back to R and paste it and then run it. So we're back here in our session. So we copy here the code. And once we copied, we simply click enter, which is then going to, so we successfully authorized ourselves. As we authenticated ourselves, we are ready to explore the rich world of Google Earth Engine datasets. So we're going to start off with the shapefiles. And here I'm at Awesome GEE Community Catalog, which really caught my attention because it has a bunch of datasets here that you can explore. And one of them we'll be exploring is earthquakes. So I'm going to simply search here for earthquake, and I get to this USGS global earthquake dataset. So I click here, and then when I open here, you can see some kind of summary for this, what it contains, what it's out there. In short, this collects all the earthquakes from 1923 to 2023 that were greater than 2.5. So here you can see also a demo of these different earthquakes with Google Map overlaid with points of earthquakes. And then you can also here see Earth Engine snippet. Now for us, what is the most important thing is that this is a feature collection object. This is important because it's going to determine the function we will use in R to call this. The second thing that we need, the second argument, is the name or the pathway to this dataset. So this is the string that I just highlighted. And this is something that you need to copy, and then we will paste it into R and use it to call it within R. The third part here is the sample code. So if you click here, a new window will open up, and here it will show you how this looks like in Google Engine. So here what you can do, you can expand this var argument. And what you can see here is, of course, the name of this data set and some other properties. You can see also the columns, what it has, and you can see also the properties of the object itself. So what it actually takes. So one of the things that is also interesting for us here is this table, what actually it has. So if I click on this, it says here that the end date is 27th of September 2023, and the first date is 1st of January 1923. Of course, there are a lot of here features. It says 980,000. Okay, once we have this information, we are now ready to go back into R, and I'm going to show you there some tips and tricks on how we can work with this feature collection. We're back in R, and over here I pasted the link to this earthquakes dataset. What I want to do next is, of course, load this collection. But before I can do that, I would like to actually load all the libraries that we will need. So I need several libraries. So I'm going to define here as a list of libs libraries that I need. So the first one is definitely the SF package. I would need this one because I would like to coerce this shapefile into an SF object so I can easily work with it in R. The second thing, I would only like to take earthquakes for Iceland. So for that purpose, I will need the national boundaries of Iceland. And the best way to get into R is using Gisco R. Then I would also like, as we create our map, to have some kind of elevation as an overlay. And for that purpose, I can use elevator package. So elevator. And then finally, I would like to create a 3D map where this elevation, digital elevation, is going to be 3D. And then it's going to have red points where all the earthquakes were registered in the last 100 years. So for that purpose, I'm going to be using the famous rayshader package. All right, so now that we have this, we can simply load them, considering that hoping that you actually have them already installed. So I'm just going to go ahead and now load them because I do have them installed. So I'm going to go ahead and do here apply. I'm going to apply to this list library function in R, which actually loads everything. And then I'm going to put here this character dot only equals true. All right. Once we actually load all of these packages, we can go ahead and first of all define the projection that we're going to be using in this tutorial for Iceland. So Iceland is a European country, and for that I'm always using a Lambert projection, but you can skip this part if you're working with a non-European country, so you don't need to define this projection. So it's going to come in the form of the WGS84 for this reference system. So I'm just going to go ahead and here define this Lambert projection that we're going to be using. Okay, and once I do that, I can then go ahead and get that shapefile of Iceland. For that purpose, I will be using GSCO-R. So I'm going to create here Iceland SF object, and I'm going to call GSCO-R, and specifically from GSCO-R, I'm going to call GSCO get countries. So for the country here, I want to get the shapefile of Iceland. So the ISO2 code for Iceland is IS. And finally, the resolution here, I'm going to be using resolution 3. All right, once we have this, our second task is to create a bounding box of Iceland so that we can capture only earthquakes that happen in Iceland. So it's quite easy to do that. So we can use SF package that we previously loaded, and its function stpbox, and here we just simply paste this Iceland SF. So this is going to create a new object, which is going to be a bounding box. Now, in order for us to have this in the Earth Engine friendly format, we do need to go ahead and transform this. So we need to transform into a rectangle. We're going to go like this. So I'm going to create a new object, which is going to be called Iceland bounds. All right, and then this one I need to use from EE, which is Earth Engine. I need to use geometry and a rectangle, as I said. So a rectangle, which is going to coerce these things into a rectangle. So we are going to provide a list here. So we need to provide several things. So west is the first one. West is basically the minimum longitude value. In our Iceland bbox, it's called xmin. So we're simply going to grab that from Iceland bbox like this. So xmin. All right. So that's the first one. The second one is south. South is the minimum latitude value. So in our case, that's ymin. So I'm going to go ahead again, just copy this, and instead of xmin, I'm going to put ymin. Okay. The third value is called east. So east side, and east in this case is the maximum longitude value. So in this case, this is called X max in our case. And the final one is north, and north here is the maximum latitude value, or in our case, it's called Y max. Okay, so once we have all these things, we can finally go ahead and actually create or fetch the data, and then fetch only for this bounding box of Iceland. Before we do that, I want to do also two more things. I want to add two more arguments to this one. One of them is called geodetic arguments, and I'm going to put it here to true, so that this actually knows that we want to have a geoshape. And then finally, the projection. I just also want to make sure that this thing knows that we want actually to have WGS84. So I'm going to say here EPSG 4326. Okay, so once we have this, all these things, we can finally use this string here, earthquake data, and load into R, but only for Iceland. So I'm going to call it here, first of all, earthquake data. And then to load here, remember, we're dealing here with the feature collection. So again, we're using EE, this generic function or argument. And then we're using here feature collection, because otherwise it's not going to know what we're doing. Okay, and then we can open this brackets. And within these brackets, we're going to be loading exactly this data set. It's that easy. Now, if you want to filter only for Iceland, what we need to do is the following. We need to add this $sign, and then we can add another argument. So if you want to filter things here, you need to use filter bounds. So that's the name of the argument. Okay, and then we can open this brackets again, and then for the bounds, we can of course use this one that we created. It's called Iceland bounds. So it's going to accept it as an argument because we coerced it into an Earth Engine object. And finally, we need to coerce this Earth Engine feature collections into an SF object. And that's going to be easy because RGE has also a function for that. So I'm going to create here an object called Earthquake Iceland. And then from rgee, I will be using something which is called EE as SF. So this is going to coerce earthquake data into an SF object. Now there's one thing here. So Iceland is pretty small, and also the amount of these earthquakes as points are going to be also very small. But sometimes maybe you want to fetch data for a much larger country, and this is where max features comes in hand. So max features here is by default it's 5,000, but here you can actually increase the size of this. All right, so how do you know if you need to increase? Well, you can simply run this rgee and then ee print and then the name of this data that you got here, and it's going to tell you how many features it has. So then you will know whether you need to increase this max features to more than 5,000, let's say 10,000, 100,000. So it's totally up to you. So in this case, I don't need to increase because it's small. I'm just going to leave this here as landmark so that you know that maybe in your case you need to change. So one more thing that I want to do here, and this is optional. Again, you can skip it if you're working with a non-European country. I would like here to transform this newly created SF object into a Lambert projection. So I'm going to reproject it, and I'm just going to pass here SFST transform and then CRS Lambert. After we got the earthquake points, I would like to get the digital elevation model for Iceland. So I'm going to call to rescue the elevator package. So I'm going to create first of all an object called elev here. And then I'm going to call elevator, and then within elevator there is a function called get elev raster. So over here I want to specify the locations for which I want to get the data. So it's going to be called Iceland SF. And then the second one is the amount of detail. I'm going to go here for 8. You can go up to, I think, 15 or 14, but because Iceland is still a country, so it's not a region or something smaller, I do tend to be kind of a conservative here. So I'm going to take a bit lower. If you're working even if it's a bigger country, you should decrease even further. And then finally, I'm going to say clip by locations here. What you can also do is you can, for example, also choose here clip by bounding box. In that case, you'll be using bbox here. So that's one thing. Once we get this data, I would like to turn it into a Terra format. So I want to turn it into a spat raster format. And also I would like to reproject it again into Lambert projection, because remember, we want the earthquake data points and the elevation data to be the same projection. So I'm going to call this new object elev Lambert. And first of all, I'm going to put this elev into a pipe. And then I'm going to coerce it into a Terra format, rest. And then finally, what I'm going to do here, I'm going to do Terra project. So this is going to reproject, and I'm going to pass here that I want to reproject to CRS Lambert. All right, so now we have both the earthquake data and the digital elevation model data in the same projection. The final thing is, in order to work with rayshader, we need to coerce this elev Lambert into a matrix. So that's going to be pretty easy. I'm going to call this lnet, this new object, and then I'm just going to use here from rayshader. There is a very convenient function to turn this into a matrix. So it's called raster to matrix. Okay, the time has come to finally create our 3D map of Iceland's elevation overlaid with earthquakes. So the first thing is to define the dimensions that we're going to use, and the safest bet here is to simply use the dimensions of that elevation raster. So I'm going to create height here, I'm going to call it h, and then I'm going to take the number of rows from that elev Lambert object. So that's the first thing. Second thing, I'm also going to define the width, and the width is going to be the number of columns of this same object. All right, and once we are done with that, we are ready then to start rendering our scene. So first of all, we're gonna use, as our height map, we're gonna use this elevation matrix, okay? And then we're gonna go ahead and first of all, define here the height shade. So this is what is going to give it a 3D looking style, all right? So here for the texture, I'm gonna go ahead and choose gray texture. So I would like this background and this hill shade to be grayish. So for that purpose, I'm gonna go ahead and actually create here a color ramp palette. So I'm gonna create based on two gray values. So one is gonna be light gray and the other one is going to be a bit darker gray. So I'm gonna be creating here a bunch of colors. So let's say 512. You can even go for a higher or lower number. So this is what we're gonna do here. That's one thing. The second thing here is that we need to add an overlay. In our case, an overlay are going to be those earthquakes. And those earthquakes are in the asset format. Rayshader allows us to use the asset format, so we don't need to worry about that. And to add those points, you need to use a generate points overlay. Okay, like this. Now that you have this, first of all, you need to define what you're actually going to use here. Well, we're going to definitely use this earthquake Iceland data because this is the one that is in the asset format. The second thing that we want to do is define the color. So here I'm going to go for red color. The third thing is the size. I'm going to go for something like 12. Here you can actually play a bit and see what is the size that work for you. So here I choose 12 because I checked and it actually 12 is fine. It worked for me. You can go up or down. One of the last things, but not least, is the extent. So this is what is going to be the extent that we're going to be using here. The safest thing here is to simply use, again, that elevation raster. And then the final thing is a must. It's a height map. So how are actually these points going to be positioned against that height map? So for the height map, you can simply use this elevation matrix. And that's basically it. The very last thing is to simply plot a 3D here. So we can use rayshader and then plot 3D. And over here, the first thing you need to provide is, again, the elevation matrix. So what is the hills or height shade? The second one is what is going to be like these spikes, or actually the elevation. Is it going to be too exaggerated or less exaggerated? So here, as you decrease the number and the minimum is 1, it gets more and more exaggerated. So those spikes become, bigger and bigger. The elevation becomes more and more rugged. So I opted here for 12 because I didn't want it to be too rugged. But you can again play with this one, increasing or decreasing it. One thing is that I don't want to have this plane around my map, so I chose here that solid equals false. The shadow equals true because I do want to have the shadow, but the shadow darkness, which actually controls how thick these shadows are going to be, I'm going to set to 1, which means they're like very, very light shadows in the background. The background itself, you can also define it. You can choose whatever you want. I like just to stick to white background, so very, very simple. What else you can do is you can define here window size of your render scene. And what I like to do here is I like to use what I already have. So window size here is in pixels because width is 5,000 pixels. I think that's too big for the screen. So you can, maybe divide by a certain number, but make sure if you're dividing with a certain number that you divide both the width and the height with that number. Otherwise, you're going to have something very skewed. One last thing is the zoom. So the zoom here, I'm going to go for, let's say, 0.515 or something like that. Here, the bigger the zoom value, it's going to zoom out more, and the lower the value, it's going to zoom in more. Then here you can also decide what is going to be the degree of under which you're going to map this. So I'm going to go for 87. So that's almost a normal degree, almost 90-degree angle of the scene. If you want those, again, that elevation to be kind of more rugged, you can go for actually a lower degree here. And then finally, whether I want my scene to be tilted or not. I don't want it to be tilted, so that's why I chose theta to be 0. A white window is going to open up, and at some point is going to render your scene, so you should be able to see a scene that looks something like this. If this is the case, you can proceed to the next phase, the final phase, which is going to be rendering this 3D object. So again, we're going to be using rayshader. So from rayshader, we are specifically going to be using a render high quality. This is the one. The first thing that you need to define here is the file name. Let's say, for example, it's going to be Iceland earthquakes.png, and extension here is also very important. The second thing is whether you want to have the preview as the object is rendered, and I say this is true, so I would like it to be. The third thing is I'm actually working with lights that have been already designed and put into an HDR file. So I will provide the link in the description below from which I actually obtained this one. And also in the GitHub repo, I will also put this HDR file so that you can then use it also to replicate this analysis. So for that purpose, I'm here turning off the light, not literally, but turning off the light option. And then I'm going to be using the environment light. So it's called environment light. And that one, for that one, I will be using the air, museum, and then playgrounds, and then 4K, and very importantly, HDR is the name of the extension of the file. All right, so I will provide this once again, so you don't need to worry about this one. It's called Air Museum Playground 4K. Okay, so then you can choose also what is going to be the intensity of this one. So for the intensity of the environment, you can actually decrease or increase. I'm going to go for 1. If you want to increase the light in the scene, you can go for 2 or a higher number. And then also I would like to rotate the original lights here. So I'm going to rotate here the environment so that my actual lights are coming from something like southwest. So the shadow is going to appear somewhere in the east. So I'm going to rotate by 90 degrees. This is of course optional, you don't need to do it. One thing that I like to turn off is interactive. So I like to put it to false because I feel that can really crash your scene if you start kind of moving the pieces in your as your object renders. Okay, so there's also one more thing, which is you can utilize the, in the case you have multiple cores in your PC, so you can also say that parallel equals true. And then finally, you can also define your width. So for that, we're going to be using this W that we previously defined, and also your height, which is called H. And this is how you do it. In today's tutorial, you learned several important lessons. First of all, how to install and set up Google Earth Engine, and specifically how to set it up in R. The second thing is how can you get certain data from Google Earth Engine. And in this tutorial, we actually use the earthquake data. And the third thing, you also learned how you can modify, crop this data for a specific extent. In this case, we created a map of earthquakes in Iceland. And then finally, we then turned this into a 3D elevation map with an overlay of all the earthquakes in Iceland in the last 100 years. I'm really curious how you take this tutorial on a journey across the world and how you actually explore further Google Earth Engine and all of its beautiful data sets. If, however, you're interested in replicating today's analysis, I prepared a link to the GitHub repo in the description box below. So feel free to check it out, to clone it, modify it, use it as you see fit. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I've prepared a few cool tutorials for you, so do check them out. See you next time.